Okay. Good morning, everybody. Let us continue, or actually recall a little bit what we did on Monday morning. So we have optimization. We have an optimization problem, which I call a primal problem. So primal in the sense that it is the problem which will be considered first. So we have an optimization problem. And I will call it P. Where we have a cost function fx, and then we have a constraint set S. So we have a constraint optimization problem, and the S is, as before, the set of points in Rn for which we have a number of inequalities. So functions gi's which constraint the variables to be in a certain part of the space. And of course, in a way, we assume that this set is non-empty. And I call the minimum value, if it exists, with P star. Then we defined the Lagrangian. Lx, and then we have the dual variables, so fx plus the sum from 1 to m ui gi x, and the dual variables ui are non-negative. And if I define, so it means that u equals a vector which has coordinates u1, u2, um. This one belongs to the part of the Euclidean space Rm where all coordinates are non-negative. So it's denoted by Rm plus. And then I define the function g of x It is also a vector with m coordinates. Like this, and this one belongs to Rm as well for every x. And in this, taking this notation in use, I can write this Lagrangian in a shorter form. So this is actually nothing else but fx plus the scalar product of u with the function gx. Then we defined the dual function. So for every feasible dual variable, we define g of u is the value of the unconstrained optimization problem, Lx u, where x belongs to Rn. And then we defined the dual problem. So we maximize the dual function with respect to the dual variables u, which are non-negative. So we maximize g of u when u is a non-negative vector. So all the coordinates of the vector u must be non-negative. And this value I denote by v star. And the dual problem, I just give the name that it is, I denote it by capital letter D. So the examples which I computed previously on Monday, we noticed that the dual function is always concave. So if I take the dual vector u such that it is lambda times u1 plus 1 minus lambda times U2, where U1 and U2, they belong to Rm plus, and lambda is something between 0 and 1. And then we start to compute what is G of U. So this is minimum of the Lagrangian, and U was lambda times U1 plus 1 minus lambda times U2 times scalar product with the vector Gx. And this one can be written. So I add here, I can write this fx in the form that it is lambda times fx plus 1 minus lambda times fx. It is completely legal operation. Then I can write this, my dual function, in the form that it is lambda times fx plus u1 scalar product with gx, like this, and 1 minus lambda times fx plus scalar product of the vector u2 with the vector gx, like this. And then we use the trivial fact that if we have two real numbers, a and b, so min a plus b is bigger than min a plus min b. So we have estimate from below that this is actually lambda times minimum of fx plus u1 scalar product with gx plus 1 minus lambda. I can take the constant lambda, which is a positive number. I can take it outside of the minimum operation because it is independent on the x variable. And here is fx plus the scalar product between u2 and gx. So on the right hand side, we have lambda times g, the dual function at the point u1, plus 1 minus lambda times the dual function of u2. And notice that this is valid for every optimization problem. It is independent what the f and g's are. So even for non-convex problems, the dual problem is always concave. And this is very important because then the dual problem is somehow always easy to solve. Even the primal problem is very difficult, very non-convex. So even if the functions, if we have even if we have a discrete optimization problem, so that we restrict our x variable in the set of integers, still the dual problem is concave, and it's even continuous. So the duality is, this is one way of saying that the dual problem or the duality is more important actually than the original problem which we are trying to solve. Then the second fact, what we observed on Monday when we solved these examples. Okay, actually we observed that we have always the strong duality on those examples. Well, that is not true, but the weak duality is always valid. So P star is always greater than equal than V star. So the minimum of the primal problem is always bigger than the maximum in the dual problem. And we speak about duality gap. If we have P star is bigger than, is strictly larger than V star. But always the solution of the dual problem provides some kind of a estimate or lower bound for the minimum of our primal problem. Because always we cannot solve the primal problem exactly, then at least the dual problem can provide some bound. What are the minimum costs? Okay, this one. So take first x belongs to the constraint set S. It means the vector gx has non-positive coordinates. Then for all dual variables which are non-negative, fx is greater than fx plus the scalar product u transpose times gx. Because in this scalar product, all the elements are, all the products are negative numbers, because the coordinates of u are positive and the coordinate of gx are negative. So the product is negative, and then when you add negative numbers together, it's even more negative. So this one is for sure valid. And this is, of course, greater or equal than the minimum of the Lagrangian functional which is defined by definition, it is the dual function. And because this is, it holds for every x and every feasible x and every dual feasible u, from this one we obtain that P star, which is the minimum of the cost function fx under the constraint set S, is bigger than maximum of the dual function with the dual constraints, which says that the coordinates of the vector u are non-negative. And this is exactly V star. And once again, this is independent on the properties of the functions f and g. So this holds for all optimization problems. The first consequence of this result is the following corollary. If x tilde is primal feasible, so belongs to the constraint set of our optimization problem, and lambda is a vector with non-negative coordinates, so lambda belongs to this set Rm plus. And fx tilde equals the dual function g of lambda, then x tilde and lambda are optimal solutions of P and D respectively. Meaning that x tilde is the solution of our primal problem and lambda is the solution of the dual problem. And once again, this is also independent on the regularity of the cost functions and constraint functions. This holds for any optimization problem. It doesn't matter which type of optimization problem we have. It's just if we have an optimization problem, f, and if we can find the dual function, So, and if we can find 2 points, x tilde and lambda, which satisfies this equality, then we know that x tilde and lambda are the solutions of the dual and primal problem. If B star is minus infinite, so meaning that the primal problem does not have a finite solution. What does it mean? It means that the dual function does not exist. If phi star is plus infinite, so the dual problem has no finite maximum, then the constraint set S is empty set. There is no points. So the saddle point was defined like this. The bare x tilde lambda belonging to Rn, or actually it is S times Rm plus is a saddle point, and let us recall what was the definition of the saddle point. So it was that maximum of the Lagrangian when we keep x variable fixed, x tilde, and mu is the dual variable. This is exactly the same as the L at the point x tilde lambda, which is the same as the minimum of Lx tilde, oh sorry, not xl tilde, but Lx and lambda is kept fixed, and we minimize with respect to Rn. So this was the definition of the saddle point. And actually we can relax here that this is exactly Rn. So x tilde lambda is a saddle point if and only if following conditions are valid. 1, Lx tilde lambda equals the dual function at the point lambda. Second, Gx tilde is less than 0. So all the coordinates of the vector Gx tilde are non-positive. And the third, we must have that the scalar product with the vector lambda and Gx tilde equal to 0. This is the first part. The second part, x tilde lambda is a saddle point if and only if x tilde and lambda are optimal solutions of B, the primal problem, and the D, the dual problem, with no duality gap. Meaning that B star equals V star. So here we have two parts in our theorem. I guess this is more or less, this answers is a proof of the theorem 5.2 and 5.3 in our slides of my or my lecture notes. And the proof. So assume first that x tilde and lambda is a saddle point. Then, by the definition of the saddle point, here, Lx tilde lambda, it's maximum of Lx tilde and mu, and so we get exactly our, because this one here is nothing else than j of lambda. So we have exactly the first condition. So one is true by definition. Then for all non-negative vectors u, fx tilde plus the scalar product of u with the vector g of x tilde sorry, the notation here. Sorry about that. So this is the optimal solution of the dual problem. So this is greater than fx tilde plus the scalar product of u and gx tilde. Because this is the here Lx tilde is bigger than this one. So it means that this implies that gx must be, x tilde must be non-positive vector, because otherwise when you subtract here, you can, if gx is has one positive coordinate. We can pick this one in such a way that the u vector in such a way that that there is a one product which is positive. So we can change this order in a different way by choosing an appropriate coordinate in u in such a way that, because this one cancels out, we have lambda minus u scalar product of gx is non-positive, non-negative. And we know that lambda here is always has non-negative coordinates. This has non-negative coordinates. The only possibility remains is that this is g of x must be negative. So from this one we get the condition 2. Taking u equal to 0, we get that the scalar product of lambda with gx tilde is non-negative. So we can subtract the values of function f. U equals to 0, so lambda transpose type g of x. So it means that if this product is non-negative and g of x is non-positive, and we know that lambda is non-negative, so the only option is that lambda, the scalar product of lambda and gx equals to 0. And this is the condition 3. And once again, notice, no information on the properties of the functions f and g are required. Not even continuity is required. So it is extremely general result. So then on the contrary, so other way around. So suppose that x tilde and lambda satisfy the conditions 1 to 3. Then we have Lx tilde lambda is less than Lx lambda. because this one is actually g of lambda. Moreover, we have Lx tilde lambda equals to Fx. Because we had the condition 3. The scalar product of lambda and the vector g of x tilde equals to 0. So here we have this scalar product equals to 0. So we must have this condition valid. But we know that this one is always greater than the Lagrangian at x tilde and mu for all u greater than 0. So x tilde lambda is a saddle point. And we have proved our theorem. Okay, there is one more step. There is no duality gap. So suppose that x tilde and lambda are optimal solutions of P and D. And in such a way that P star is equal V star. So then we know that G of lambda is less than Fx tilde plus scalar product of u with G of x tilde. And this is less than Fx tilde. We assume that there is no since there is no duality gap, we get that g of lambda equals fx tilde. And there we get that x tilde lambda is a saddle point. And conditions 1 to 3 are valid. So now we have proved all statements in our saddle point optimality criteria. So we have proved that if x tilde and lambda are optimal solutions of P and D with no duality gap, then x tilde and lambda is a saddle point, and which is equivalent with the conditions 1 to 3. And once again, remark, no assumption on the function g of f and g functions. And actually I can relax. I took the constraint set for primal problem. So it was the ambient space was Rn. Actually, we can relax that one also. We can take any set. The dual variables, they must live in this space Rm plus. So this duality in a way extends our optimization to more general optimization problem than just convex optimization. But then if we introduce more regularity, so for example, that the functions are differentiable. So suppose that x tilde lambda Rn times Rm plus satisfy the Karus-Kuhn-Tucker conditions. Okay, I assume let us take one more, just a little bit more. So let us assume that we have a convex case. In the Karus-Kuhn-Tucker conditions, the gradient condition gradient of f x tilde plus the scalar product of lambda times it's the gradient of the gx tilde. So this is actually, it is nothing else than this one here is the short form notation for the sum lambda times gradient of gi x tilde. So the gradient condition, this is equivalent with the condition Lx tilde lambda equals minimum of Lx lambda which is the same as the dual function at lambda. So it means that the Karus-Kuhn-Tucker conditions imply the conditions 1 and 3 in the saddle point criteria of optimality. And then we get this, finally, I guess it is here already. So we get here that the following theorem. F G1 to Gm convex differentiable and x tilde lambda satisfy the Karus-Kuhn-Tucker conditions, then x is the solution of B, lambda is the solution of the dual problem, and we have B star equals B star. So strong duality. So these two theorems justify our actions on Monday. So when we computed, we had the primal problem, we computed the dual function, dual problem, solved the dual problem, and then obtained that this, because everything was convex, the solution from the solution of the dual problem, we get the saddle point, and we get also the solution of the primal problem. So actually now we have proved in a different form the theorems 5.2 and 5.3. And let us take an example where the common example in practice, we have a quadratic functional. And at this point, I assume that this quadratic functional is symmetric, positive definite, and B is just some given vector. And the constraint set is intersection of half spaces. So we have a matrix C with m rows and n columns, and we check the points where Cx is less than vector D. So the coordinates of the vector C times x, all the coordinates are less than the corresponding coordinates of the vector D. And of course, this constraint set, because it is an intersection of half spaces, it's hard to find that this kind of a space is empty. But it is, of course, it is possible that it is empty set, but in practice, this is always non-empty, meaning that the constraint set is non-empty, meaning that the dual function must exist. So that we can always define a dual problem. Moreover, the quadratic functional being symmetric and positive definite, this function is convex. And the constraint set is also convex because the constraint functions are just linear functions actually. So we are in the convex optimization setting. So the point which satisfies the Karus-Kuhn-Tucker condition is the saddle point, and so on. And we have the strong duality. So there is no duality gap between the solution of the primal problem and the problem of the dual problem, solution of the dual problem. The Lagrangian functional is here. So I have written it in the different form. So the primal problem has always a unique solution, because here we have just, there is some, if x is kept, is a variable and mu is kept fixed, this is just some constant. This is also a constant vector. So we have unconstrained optimization problem, which is where it's quadratic and the matrix A is, the Hessian matrix is positive definite. So there is a unique solution for every mu. Not necessarily. If you can justify, for example, that it is strictly diagonally dominant, then it is positive definite and so on. And because this condition is valid, then we know that there must be at least one saddle point. And uniqueness of the saddle point is equivalent with the uniqueness of the dual problem. So we have to verify that the dual problem has a unique solution. So let us compute what is the dual function. This is quadratic. This problem, the minimization with respect to x variable, provides the unique solution x mu, which is the solution of the linear system of equation. And we can solve it. X mu equals inverse of the matrix A times the vector B minus C transpose times U. And we insert this x mu in our Lagrangian functional because it's the value of the dual function at the point mu. So we know that the ax mu scalar product with x, ax mu equals p mu. So ax mu is p mu. And okay, the c mu is dropped out here, but so this is 1/2 times p times x. This is minus p, so it's altogether minus 1/2 b mu scalar product with x mu. And then we have, I have forgotten here, it is the x mu, but x mu is nothing else than this minus mu transpose time d. It's just a scalar product with mu and d. And then b mu was b minus c transpose times mu. And x mu was A inverse times B minus C transpose times mu minus mu transpose D. It means that if I multiply it by minus G, it is minus G of mu. So minus of the dual function is 1/2. And then you make the computations here. So you get mu transpose times C times A inverse times C transpose times mu. And then you have a vector C times A inverse times B minus D scalar product with mu. And this part is quadratic. We have a constant term, which is 1/2 P transpose times E times P. The matrix here is symmetric and positive definite if and only if the rank of C equals M. So all the row vectors of the matrix C are linearly independent. Then the maximization problem of the dual in the dual problem has a unique solution if and only if the rank C equals M. Okay, this one we considered. So then, what is the interpretation of the duality? So the X variables describe the operation mode of a company. Labor costs, material costs, energy costs, transportation costs, whatever you can find. And you sum them all together, you get the operation cost is the cost function f of x. Then we have constraints. So we have some resource or regulatory limits. So for example, we have a limitation of labor. And in Finland, there is a rule that we cannot work more than 37.5 hours per week. So there is a limitation how much every worker can work. And there is also a limitation of the labor. How much workers do you have available? Then you have a limitation, for example, the storage, limitation on the raw materials, whatever you can find. And then they are in these constraints. And then the optimization problem is find the optimal operation mode for the company under given limitations. It is our primal problem. Then take the case that I can violate the limits. So for example, there is regulation that I cannot put any waste material in the nature. So if I'm a criminal capitalist, then I don't care to these limitations. I violate them. I put the waste of my products in the nature and I don't care. But then the organized society finds it out and they make a penalty. And assume that the penalty is linear amount of violation. So this is now non-negative, so I violate the, so this is not anymore, for example, it is positive number, it is not anymore negative. So if UI is the money which I have to pay, this is the penalty altogether. So if this product is positive, then the company pays a penalty. And if this one is negative, so I'm not exceeding the limits, I receive the money because I can sell my capacity to other companies. So, for example, in this, we have this. I think it is. Is it only in European Union? But I think that it should be worldwide. That, for example, that there is a Finnish companies. They put in the air carbon dioxide, and there is a penalties. There is a certain amount of carbon dioxide you can put in the air. But if you don't put that much carbon dioxide in the air that is permitted, you can sell your carbon dioxide resources to some other company. So I can earn money from this carbon dioxide regulations or limitations. Now, what is this UI? It's the dual variable in our optimization. So the dual variable is the price in euro for breaking the constraint per unit. And the total cost is then fx plus u transpose times g of x. And the dual problem is, of course, maximize this. Yes. This is possible, yes. So this is somehow this kind of a zero-sum game. At some point I give you, and then at some point you give it back. So, and if we have a weak duality, the optimal cost, if violations are allowed, is less than the original situation, even with the most unfavorable prices. So it doesn't matter how much I violate the constraints, or because the optimal cost is achieved without more or less the constraints. If we have a strong duality, the dual optimum lambda is the set of prices for where there is no advantage for the company to violate the constraints. And that's the reason why they are called in economics the shadow prices. And of course, the criminal people, they want to have this weak duality. But for the government wants to have the strong duality, or people who wants to obey proper rules, because then you have to follow the rules, because it is the best way of running the company. So regulation is important. Okay, then if we include these equality constraints, once again, we can introduce the Lagrangian functional. The Lagrangian functional is once again concave, or the dual function is always concave. We have the Karuskun-Tucker conditions, but the Lagrangian multipliers or the dual variables which corresponds to the equality constraints, they don't have any sign limits. So the sign limits corresponds only the inequality constraints. And the dual function can be defined in the same way. It is always concave in the u variable, but not in the v variable. But of course, inequality or equality constraints can be transformed into inequality constraints just by taking h is bigger than 0 and minus h is bigger than 0, or vice versa. And then I start already the practical point or algorithmic point of duality, and it is the computational method, how to find the solution of our optimization problem. So we have a primal problem where we have a cost function f, and then we have a set of inequality constraints. The objective is to construct an algorithm which computes the approximate solution of this primal problem. But at the same time, it computes the approximate solution of the dual problem. So it computes also the value or the approximation of the value lambda. And how we do it? We consider the dual problem. We are actually solving the dual problem all the time. And we apply the gradient method because it is, even though it is constrained optimization problem, we use the gradient method for solving it. But because in the gradient method, it is possible that our approximation goes outside the feasible set of the dual problem. So one of the coordinates is negative. Then we use simple projection operators. We project lambda, the coordinate, I coordinate of this lambda vector equals lambda I, if lambda I is non-negative, and if lambda I is negative, then we replace it by 0. So it is a simple projection operator. We always, at every step, when we make the gradient step, we project the point to the correct constraint set. So we generate a sequence of dual variables, lambda k, where lambda k plus 1 is first lambda k plus step length times gradient of the dual function at lambda k. And if this vector has one negative coordinate, we replace that one by 0. And if the coordinate of this vector is positive, it is kept. So very simple. Now, the step length. This is, there I make a little, it's not completely gradient step. I take a fixed, more or less fixed step length always. So rho k is small positive number, but I can change the number a little bit, but usually I keep it fixed. Now the problem is, what is the gradient of the dual function? So let us take 2 points, lambda and lambda plus mu. They are 2 points in Rn plus. They are dual feasible variables. X lambda and x mu plus lambda are the solution of this unconstrained optimization problem. Minimize the Lagrangian when alpha is kept fixed with respect to x and alpha is lambda or lambda plus mu. Then we have the inequality. So if we keep lambda fixed, then Lx lambda is the solution of the minimum problem when alpha equals lambda. So for sure, this one is less than the value of the Lagrangian at the point x lambda plus mu and lambda. And vice versa. If I keep lambda plus mu fixed and minimize with respect to x, I get this optimal solution here. It's the minimum. And for sure, it is less than Lx lambda and lambda plus mu. So here I have on the right-hand side, sorry. So if I take the subtraction, so here is g of lambda plus mu. On the right-hand side, we have g of lambda and then the scalar product. Because if you put here alpha instead of alpha, lambda plus mu, and then you have g of x lambda, there is exactly g of lambda, the dual function at the point lambda, and then the difference here is the scalar product of mu and g at x lambda. Then if you take here, there is g of lambda, and there you put here yes, mu minus mu. So you get here g of lambda plus mu minus u is bigger than mu times g of x lambda mu. So we can estimate the difference of the dual function at the point lambda plus mu and the value of the dual function at lambda. So the upper bound is mu, scalar product of mu with j x lambda, and scalar product of mu at the point with the vector g x lambda plus mu. And then it says that there exists a constant theta between 0 and 1, that we have this equality. So it means that if these function, these small g's are differentiable, this one is very small when mu goes to 0. So it means that this vector g at x lambda is nothing else than the gradient of the dual function at the point lambda. And notice, I have never computed the dual function. Actually, I don't need the exact form of the dual function. I need only the information that the dual function exists. It is differentiable, and I can compute the gradient of the dual function. Only what I have to do, I have to compute the unconstrained optimization problem at every step. I have to compute fx, the minimum of fx plus lambda transpose times g of x. And then I compute the gradient of the dual function. So in this way, I get the Usawa algorithm. Choose any lambda 0. Define a sequence of pairs xk and lambda k. So first I compute x0. It's the minimum of with the cost function fx plus lambda 0 scalar product with gx. This is an unconstrained optimization problem. And for that, you can use any algorithm, Newton gradient, conjugate gradient, whatever, and you obtain xk. And then when you have computed xk, you compute the new dual variable, lambda k plus 1. It's lambda k plus 1. You perform the gradient step with the step length rho k, and then perform the projection that you are remaining in the dual feasible set. And then you iterate, you make the iteration. And at some point, xk converges towards the solution of the primal problem. Lambda k converges towards the solution of the dual problem, hopefully. But let us continue from that on Monday morning.